Hello, good morning. Good morning, everyone. It's a pleasure to me to welcome you in this webinar series. My name is Pilar Navarro. I am the director of Expquimia, and Neurosurface, together with leading the business unit from Chemistry and Life Science in FIRA Barcelona. I'm very glad that you could join us in this webinar, Stainless Steel from Dream to Reality, which is the prelude to the Advanced Materials and Degradation Congress that will be held next April 21st, 22nd, 2021. The inscriptions are open and don't miss this opportunity. Also, let me introduce, and it's a pleasure to me to introduce to Mr. Meseguer, moderator of this webinar. Currently, he is the principal investigator at Leitat within the Surface Chemistry Division, SurChem, as the head of the pretreatment group, developing industrial, national, and international projects focused on different topics with the surface treatment of metal, as well as the treatment of metal parts manufactured by IM in 3D printing. Previously, he was working in the R&D department in the company Fuchs in metalworking. He also have been for more than 10 years the R&D department of the Texas company, developing the formulations of autonomous sheets and well, another type of surfaces as you can imagine. Well, it's a pleasure to me to give the floor to right now to Toni. Toni, it's a pleasure to have you here, and also thanks for all the speakers from different nationalities and different backgrounds, and also Mr. Groysman for all the coordination from this kind of webinar and congress. We see you a little bit later in the discussion part. Okay, thanks very much, Toni, and the floor is yours.
Okay, thank you very much, Pilar, for the nice introduction. Good morning to all of you. Welcome everybody to this webinar framed within the unprecedented webinar series. Thanks to Expquimia, Plus, and Neurosurface for giving us the opportunity to carry out this webinar. Today, as Pilar said, we will talk about stainless steel from dream to reality as a prelude of the Advanced Materials Providing New Solution Congress that will take place on April 20th and 21st of this year, 2021. We encourage you to register and participate in this event. And in this webinar, we will talk about successful stories and challenges of using stainless steel in the chemical, food, and pharmaceutical industries. Thank you very much to take time to join us today. My name is Toni Meseguer. I'm responsible for metal pretreatment team within Surface Chemistry area and Leitat Technological Center. And we are lucky to be able to have the guests of the highest level today. For today's presentation, we will have the participation of Dr. Alec Groysman, President of Honor of Association of Chemical Engineers and Chemists in Israel, Dr. Claus Qvist, Metal Specialist and Stainless Steel Geek at Damstahl, Dr. Herzl Yeheskeli, R&D Manager at the Leitat Group, and Dr. Tatiana Henrich, Application Engineer, Sales, Oil and Gas, and Additive Manufacturing at BDM Metals International. So the agenda for today, we will start with the Dr. Alec Groysman, who will talk about the myths about stainless steel. Secondly, Dr. Claus Qvist will talk about the use of stainless steel in pharmaceutical and food industry, hygienic design, and the end of the all the new problems and their solution. Then Dr. Herzl Yeheskeli will talk to us about surface treatments for real-life stainless steel components. The last talk will be given by the Dr. Tatiana Henrich, and she talked about additive manufacturing for chemical process industry, opportunities and limitations. Finally, we will have enough time to answer questions of the audience. You can write your question during the presentation in the corresponding column on the right side of your screen. And let's start with the first speaker. Dr. Alec Groysman graduated from the Chemical Technological University named after Mendeleev in Moscow. He received his PhD in physical chemistry and corrosion. He has experience in corrosion control, and corrosion monitoring from 1976 in the refining, oil and gas, and chemical industry, and teaching the subject of corrosion. He has lived in Israel since 1990. He worked for 22 years for oil refinery Haifa, and at the same time taught corrosion science and technology in different universities as Technion in Haifa, Bar-Ilan University, and Tel Aviv University, and College of Engineering like Carmiel in Israel. He's an honored president of Israel Association of Chemical Engineers and Chemists. He deals with kinetics and thermodynamics of corrosion processes, online corrosion monitoring, choice and use of corrosion inhibitors, coring systems, selection of appropriate alloys for corrosive service, and failure analysis. He has special interest in corrosion education and in searching for relationships between corrosion, art, history, and philosophy. And now, without further ado, I shall give the floor to the first speaker, Dr. Alec Groysman, who will talk about myths about stainless steel. Dr. Groysman, please, you can start with your presentation.
Thank you. Is this okay? Do you see? Hello? Tony? Tony, is it okay? Tony?
Yeah, it's okay.
It's okay. I begin. Yeah. Okay. Thank you very much, Tony, Pilar, yes, for this introduction and for organization this Congress and the first prelude. Yes, I appreciate your initiation. I was born in the small town of Yalta in Crimea, studied in Moscow Chemical Technological University, named after Mendeleev. I worked in the city of Astrakhan in the south of Russia. I moved to Israel in 1990, and I have been living in Israel for 31 years. This is my capital, Jerusalem. This is Haifa, the city where I work. And I live in a small village of Shania in Lower Galilee. I have known Pilar Navarro, the director of FIRA Barcelona, for about 7 years. When Pilar asked me several months ago, which topic is interesting for you and for people who work in the chemical industry, I remember the beautiful sculpture made from stainless steel by a sculptor Roy Zinger in Jerusalem Center, statue of a big mirrored globe. Then I looked in our kitchen and revealed shiny kitchenware made from stainless steel, aesthetically pleasing. Really, I have been dealing with stainless steel objects for 45 years of my career. Without hesitation, I suggested talking about how people came from dream to reality with the application of stainless steel. However, many of the things engineers think they know about stainless steel aren't true. In order to begin our short journey into the world of stainless steel, we should begin from the definition. Stainless steel is an iron-based alloy containing more than 10.5% chromium and a maximum of 1.2% of carbon. Stainless steel is steel that does not corrode. This graph shows that when we add above 10.5% of chromium to iron, this alloy does not corrode in a pure atmosphere. It took about 20 years to prove that tenacious chromium oxide film was responsible for high corrosion resistance. And Ulrich Richardson Evans from England and Ulrich from the United States, they proved this in the 1930s. And I'd like, during my life, if euphoria finished quickly, during my life, I go with many legends and myths about stainless steel. Here I choose 7, similar to the 7 wonders of the world. Each of you can add new myths. We can read in some books that this was the discovery and not the invention of stainless steel. The second myth is that all stainless steel are the same. And the third one is that stainless steel doesn't rust. The fourth, stainless steel is not magnetic. The fifth, stainless steel cannot be used in seawater. The sixth, stainless steel is hard to clean. The seventh, Stainless steel is expensive. So let us try to demystify the mixed conceptions as succinctly as possible. Even the discovery of stainless steel is shrouded in myth. According to legend, stainless steel was discovered in 1913 by British metallurgist Harry Burley when he noticed that some samples of an experimental alloy he was planning to throw away had not rusted after sitting on a shelf for several months. In fact, Burley knew what he was doing. It had been known since the 18th that adding chromium to steel increased its corrosion resistance, and the number of inventors around the world had already developed materials that would be considered stainless steel today before 1930. A year before, in 1912, a famous American metallurgist, Elwood Haynes, inventor, automotive pioneer, and entrepreneur, who founded the Haynes Steel Company in the same 1912 year, created martensitic stainless steel. Burley's main contribution was realizing that these steels could be used for table cutlery. It was Ernst Stewart, one of Burley's associates in the cutlery business, who came up with the term "it stains less stainless steel." In the same year, 1912, two German metallurgists, Bene Strauss and Eduard Maurer, created austenitic stainless steel with the name Nie-Roster, from the German nicht rostender Stahl, non-rusting steel. Let me share with you our Israeli joke regarding the names of stainless steel. A director of one plant invited a corrosion engineer to his plant and asked him, "Which kind of alloy do you recommend for this reactor?" An engineer answers him, "Stainless steel 316. A director tells him, "It's a pity that I did not invite you a week before. We have just ordered the roster." In the same 1912, two Americans, Christian Danzizen and Frederick Beckett, invented ferritic stainless steel. Now, I invite you to decide who created stainless steel the first. The next myth: all stainless steel is the same. There are 5 groups according to crystallographic structure and about 180 types of stainless steel. Ferritic with body-centered cubic, when adding nickel; austenitic with face-centered cubic; martensitic body-centered tetragonal; duplex 50% ferritic plus 50% austenitic; and precipitation hardening, pH, and each type has its own properties. Let me share with you one problem with the designation of stainless steel. It's not easy to understand the mess in the names of stainless steels. Please review 1304 stainless steel, which has 36 names. This is Prime Minister of Spain, Pedro Sanchez. The term stainless steel is responsible for another myth, the belief that stainless steel does not rust. In languages other than English, the confusion can be even worse. For example, in Spanish, stainless steel is called acero inoxidable, unrustable steel. We may identify 15 corrosion phenomena that can occur with stainless steel. Wow! And you see pitting, crevice, galvanic, intergranular, stress corrosion cracking, sulfides, stress corrosion cracking, corrosion fatigue, microbiological induced corrosion, and so. Wow! And we continue naming stainless steel. Wow! The most interesting phenomena is rouge. Sometimes these stains are named T-staining. You see here, stainless steel resists corrosion better than most other alloy because of a very thin, colorless passive layer that forms spontaneously on the surface. When the passive layer is breached, it usually forms again spontaneously. In some environments, such as very close to the beach, where there is a lot of salt in the air, the passive layer may not be able to form, and some corrosion may take place. Rouge is commonly used term for the visible corrosion product of stainless steel. It can be composed of several forms of iron oxides, with red ferric oxides being the predominant form. It can be due to iron contamination of stainless steel surface, due to welding of non-stainless steel for support columns, or other temporary means, which when welded out leaves the form chromium area. Stainless steel is thus an oxymoron, like a true myth, or amazingly awful, in that it can stain, corrode, and rust under extreme atmospheric or contaminated environments. If people do not know under which conditions stainless steel is truly stainless, this can lead to catastrophic circumstances. I remember well when I began working as a corrosion engineer at an oil refinery, and we had to examine a material of heat exchanger tubes. One mechanical engineer took a magnet for the examination. Do engineers correctly identify stainless steel, observing that the magnet is not attracted to the steel surface, and conclude that this steel is stainless because it is non-magnetic? But there are 5 types of stainless steels according to crystallographic structure. Only austenitic stainless steel that has not been worked hardened is non-magnetic due to its nickel content. Austenitic stainless steels are used for non-magnetic applications, for example, mass spectrometer or magnetic resonance imaging, MRI. Other types of stainless steels are magnetic. Therefore, the use of a magnet can be applied only to decide if the steel is austenitic, and cannot be used to define ferritic, martensitic, duplex, and PA stainless steel. Let me share my personal note. Austenitic stainless steel is a natural, unusual, metastable condition state. At room temperatures, ferrite is stable. The addition of nickel and manganese turns austenitic steel stable at room temperatures, but the austenitic can become magnetic when they are deformed. Cold work and welding are liable to increase the amount of martensite and ferrite respectively in the steel. After deformation, it is well hardened steel. Try putting a magnet in the corner of stainless steel seam. Some magnetism can usually be detected. If you open old textbooks on corrosion 20-30 years ago, you can read the stainless steel cannot be used in seawater. Really, at the beginning of the 1990s, one engineer at our oil refinery showed me a ball valve made from stainless steel 316 that mounted in the firefighting line containing Mediterranean sea water failed because of leakage. This ball valve, you see, served only 3 months. Pitting corrosion occurred exactly according to the textbook. We may see such tables with maximum chloride content without pitting. However, in seawater, chloride content is hundreds more. Another engineer informed me that at his unit, stainless steel 317 tubes have been using for 5 years with cooling water of high salinity without problems. Then another engineer, who was a captain of a submarine, told me that submarines were made from stainless steel and were used in seawater without any problems. I understood that stainless steel can be used in seawater only under conditions of circulation, that is, under the constant moving of seawater. Pumps, heat exchangers, pipes can be used in contact with moving seawater. During its stop, equipment should be drained and rinsed. About 50 years ago, the pitting resistance equivalent number was introduced. Everyone can calculate this number defined by the content of chromium, molybdenum, and nitrogen. Nowadays, stainless steel alloys for seawater must have a pitting-resistant equivalent number more than 40. Usually they have 6% of molybdenum and 0.1% of nitrogen, and critic pitting corrosion temperature, which can be examined according to STM G150, was introduced apparently the same 1970s, which also can show which stainless steel can be used in sea water. Many times I have heard people complain that their supplier has swindled them if a stainless steel part shows signs of rusting. This is 316. Often, when stainless steel appears to be rusting, it has actually been contaminated with carbon steel, which rusts, of course. The secret is to fabricate the stainless steel in a dedicated area and make sure there is no contamination with carbon steel from tools, equipment, and store fixtures. And if there is carbon steel contamination, treat the stainless steel with 3 consecutive steps: degreasing, alkaline cleaning, acidic cleaning, pickling, and passivation. We should remember that passive film, chrome 203, is formed only on a clean surface stainless steel. You will listen to the lecture of my colleague and expert in this field, Herzl Yehezkeli. In fact, stainless steel might be one of the easiest alloys to clean. Never use abrasive scrubbing clothes such as Scotch-Brite pads, and this will scratch the surface of the material. Stainless steel is still widely considered to be one of the most hygienic materials to use because it is easy to clean and sterilize. It's often the topic choice for use in commercial kitchens and medical facilities. I give this credit to my colleague and friend, Dr. Claus Qvist from Denmark. And now I finish with a question. It is the end. Oh, I will show you the fairy tale, Ugly Duck by Hans Christian Andersen. Klaus, you like this person, yes? Also from Copenhagen, Denmark. And in this ugly duck, small ducklings say, oh, how green the world is! Still wood. Now they were much more spacious than in a shell. And their mother said, don't you think that the whole world is here? What is there? It stretches far, far there, beyond the garden, beyond the field. But to tell the truth, I have never been there since my childhood. The world of stainless steel is also endless and eternal. Thank you very much.
Thank you very much, Dr. Groysman. Very interesting and clarifying presentation. And I shall give the floor to the next speaker. The next speaker is Dr. Herzl Yehezkeli, and we talk about surface treatment for real-life stainless steel components. Dr. Herzl Yehezkeli is bachelor and master scientist in electrical engineering. He is R&D manager in a Leitat group. He has over 40 years on experience in telecom, datacom, R&F, and EM, remote sensing and signal processing, materials, engineering, and metallurgy. That's experience in technology, technology management, and operation management. Please, Dr. Herzl, can you start with your presentation?
Yeah, thank you for the introduction. Let me share my screen. I hope you can see it.
Yeah.
Okay, very well. So welcome everybody. My name is Herzl. I'm the R&D manager of the Leitat group. Leitat group is comprised of 3 companies. As I wrote here on the right-hand side, Leitat Polishing, does all kinds of Electro-Polish and similar processes. Limat Chemistry, which develops and manufactures cleaning and special materials for the stainless steel industry, and Schwarz Almog, which is a company that does the coating and surface finishes, all sorts of gold, silver, nickel plating, and other plating for metals and polymers. I will discuss today surface treatments for real-life stainless steel components. And I will start my lecture today with 3 slides regarding what happens on metallic surfaces. I'll discuss in a short phenomena. I'll discuss in short how to manage the situation at the metallic surfaces. And I will list several applications where the surface behavior is critical or very significant to the application. Later on, I will share some slides about a specific group of materials, namely stainless steel, and processes. I will discuss chemical passivation and Electro-Polish. And later on, I will discuss 4 or 5 use cases as examples of tailoring solutions for customer needs. Let's start. Metal surface is a very interesting place or location. It is where all sorts of interaction phenomena take place. Mechanical phenomena like friction, erosion, abrasion, chemical phenomena like corrosion, which we will discuss a lot, mechanochemical phenomena, which I will mention a few, capillary and wetting, hydrophobicity and liquid shedding, absorption and adsorption of liquids and gases, welding, galing, etc. And there are other types of phenomena like mechanochemobiological, adherence or sticking, infections, and the creation of biofilming. These are all sorts of biochemical, biological phenomena. And last but not least are electromagnetic phenomena, depending on the wavelengths like microwave, millimeter wave, infrared, visible, or UV. You have all sorts of phenomena like absorption, reflection, spectral filtering, coloring, and I will mention at least one such a phenomena in relation to one of the applications that I use as a use case. Now, surface treatment are processes that are aimed to set the above mentioned interaction phenomena, either maximize it or minimize it or optimize it. There are thermal treatments like hardening. There are mechanical treatments like shot pinning, and there are others. And there are finishing treatments, which we at Limat Group are dealing with. Some of them encompass removal of material like abrasion, mechanical polishing, electrochemical polishing, lapping, honing, etc. Some refer to chemical changing of the surface, like chemical conversion, passivation, activation, and some are adding or covering the material with coating or painting, etc. We at Limat are dealing with all these 3 treatments, types of groups of treatments. Let's talk a little bit about applications. There are many applications that require specific focus on surface aspects, not only the topography, but also other aspects like hardness. And these are a list of applications like roll bearing or ball bearing, armor piercing weapons, and armor protection. Hardness is very important, and it happens on the surface. Corrosion resistance. In the medical and food industries, we use tools, we use piping. Exterior applications and especially marine applications require corrosion resistance. This happens on the surface. The number 1 here shows that I'm going to refer to this as in one of my use cases later on. Friction. Sometimes you want to maximize it, sometimes you want to minimize it. Like friction bearing, roll bearing, Shaft encoders, you want them to slip nothing, so you want to maximize the friction. And slip rings, you want to minimize the frictions. It all happens on the surface. Hydrophobicity, painting systems and wetting systems, especially in exterior and marine applications, are very important. Also happens on the surface. Dimensions accuracy, like gear systems and tight fit for pressure fit or for hermetic sealing, this all requires accuracy of dimensions, and this happens on the surface of the metal. Roughness minimization. We need, in clear rooms, we need the minimum roughness possible for ease of cleaning. This is relevant for pharma and food systems. In other systems, we want laminar flow instead of turbulent flow, so we want the roughness to be minimized. Also happens on the surface. Electromagnetic losses. Usually we want them to be minimized depending on the wavelengths. Some examples are waveguides, filters, antenna feeds, etc. When we move to light reflection, in some cases we want it to be maximized, like brightening. So this happens in optics. We want to build mirrors or increase the illumination efficiency and reflectors. Number 3 here refers to the fact that I'm going to use one of my use cases in this area of reflectors. Now there are all sorts of other applications like pathogen sterilizations in UV or heat removal and avoidance like IR radiations. So all this is maximizing the light reflection on the surface. Sometimes you want to minimize the light reflection. You want to blacken or absorb light, minimize stray light in optical systems, camouflage, absorb heat. So you want to blacken the thing. Again, happens on the surface. Coloring is yet another example. There are many applications, some functional, some decorative, and you have all sorts of organic or inorganic or polymer pigments, and there are physical colors which we will not get into. All happens on the surface. Adhesion. Adhesion is something that you need. You want to activate the surface, roughen the surface in preparation for coating, like glue preparation, solder preparation, paint and coating preparation. All happens on the surface. And last but not least is polishing. You want to minimize the topography or the roughness of the surface. For example, to minimize the crack initiation for fatigue resilience, which is yet another application that I'm going to touch on later on. And so with that, I will move to the main part of the presentation, which will deal with specific materials, namely stainless steel, and specific processes that are aimed for achieving specific goals on the surface. I'm not going to delve into this list because you are going to hear it later on the presentation. So let's go to what stainless steel is. As mentioned by Professor Groysman earlier, this is a iron alloy that includes more than 10.5% of chrome. And the common commercial synonym for this is Nirosta, the German name. This is the usual composition of stainless steel, but there are many types, and we'll touch on that a little bit later. Nickel is an addition that in some cases, richer nickel content beyond iron and chrome can improve corrosion resistance and brightness. But if you need lower cost alloys, you need to lower the nickel content. And there are other specific merits like allergy for personnel. So nickel is not part of the game. We'll focus mainly on iron and chromium. So what about stainless steel corrosion? As Professor Groysman mentioned, stainless steel corrodes much less than other steels, but it definitely corrodes. And there are three ways to reduce or prevent the corrosion. And if you remember, corrosion is the oxide of iron, ferrite 2O3. So there is a slow process, which is a natural process. If you put stainless steel in a clean and low humidity, low dust environment, it will eventually grow a buildup of protection layer, which we will discuss in a second, and will stop corroding. There is an expedited process called chemical passivation. We do it in a standard acidic solution, and I will discuss it later on. And there is a both expedited and thorough process, which is called Electro-Polish. It is an electrochemical process, and we will discuss it quite deeply later on. So what is the trick? The trick is creating a thin layer of chromic oxide, Chrom 2O3, on the surface. This layer protects the material from further oxidation and rusting. It actually hides the iron from the free air and prevents the classical rust, which is the ferrite 2O3. And it's a very, very thin layer. The thickness of it is up to 30 angstrom when it is chemically passivated, and up to 150 angstrom, which is electro-polished. Roughly, this is the number of single atom layers, because an atom is in the order of magnitude of between 0.8 to 2 angstrom. So this is roughly 30 atoms, and this is roughly 150 atoms. This layer has a natural healing merits in case of mechanical scratches and other damages, because it will start growing with the environment oxygen again and make this protection available again. Now, it is recommended to preserve the stainless steel during service against rust in light situations, early life, just by rinsing in water. In heavy rusting, progressive, by rinsing with specialized liquid agents. This is called field passivation, and I will touch one of the applications like this later on. So let's talk about chemical passivation. It's a chemical treatment for increasing and speeding the resistance of stainless steel against rust. We enforce the acceleration of this chromic oxide buildup using two classical acids, a very weak acid called citric acid and a strong acid called nitric acid. This passivation causes the stainless steel to become passive or inert or oxygen agnostic, so it will hardly interact with the oxygen in the air and will not corrode. And as I mentioned earlier, this is the generation of the chromic oxide. It hides the rest of the material behind it and prevents the free iron from interacting with the oxygen in the air, and hence will not corrode. This is an example of stainless steel plate that was put into, or partially put into citric acid, and you see that this area is passivated, it does not corrode, does not show stains of rust. Electro-Polish is a different process. It's a combination of electrical and chemical process. We can see here a bath with an electrolyte. There are two cathodes put in here, and the workpiece to be polished is connected to the anode, the positive pole. Usually we use quite safe low voltages between 7 to 12 volts from a DC source with a controlled waveform. Usually it's a step waveform. Some cases it is a ramp waveform. I will not go into these details. The electrical action is that the metallic workpiece, which is connected to the anode, is charged with positive electrical charges, and they are being attracted to the cathodes, the counter cathodes, via the conducting electrolytic solution. And this solution is usually a mixture of several acids, some weak acids like phosphoric, and some strong acids like sulfuric. This is an electric action, but it is combined with chemical action. Some of these metallic ions that leave the workpiece towards the cathode, they are bonded to the electrolyte chemicals, and the compounds are sedimented in the solution and being removed from the surface of the workpiece, and this is the polishing effect, this removal. Why is this process so recommended? So first of all, how much are we removing? Usually we remove between 5 to 20 microns of material together with stains and minor scratches. I will talk about scratches later on. The nice thing about it is that the metallic impurities absorbed during manufacturing, like free iron, if present on the surface, they are all removed from the surface and released to the solution as part of this electrochemical process. This passive protection layer that is being built on top of the workpiece is highly resistant to corrosion, even in very corrosive environments. And I will show the difference between classical passivation or chemical passivation to electro-polish later on. And of course, because of this removal, the layer is also bright and smooth. Unlike mechanical polishing, electro-polish does not involve stresses or all sorts of forces that create stress in the material, and thus prevent surface brittleness, which is a good merit. And the resulting surface is very healthy in terms of metallurgy, because all the impurities and oxides are removed. It is clean, smooth. No organic materials can stick to it or can less stick to it. And all the original alloy merits are preserved. And as you can see here in this picture, there is no noticeable brightness thanks to the light reflected from the smooth surface and the nickel content below the chromic oxide layer. Let's talk a little bit about roughness. First, some examples. These are the same workpiece before electro-polish and after electro-polish, and you see the difference. Again here, this is before electro-polish and after electro-polish. And again here, before and after. Definitely, we know that this roughness is being smoothed after electro-polish to being much smoother than before. And the question is how much? So roughness reduction in classical electro-polish, which I'm discussing today, enables between 1 to 2 ISO grades, like from N8 to N7 or from N8 to N6, which is equivalent to between 50% to 75% reduction in RA, in microns or micro inches, due to this to some surface copying effect. And this is what can be achieved with classical electro-polish. There is a future type of electro-polish which we are now investigating, and it will be available in 1 year time in our R&D, which will be able to take us even from rougher surfaces like N9 to very, very smooth surfaces like N2 or N1. This is relevant to sealing on contact between metal to metal or metal to polymer, and also to prevention of crackiness for fatigue performance, which I will discuss later. But this is not available as of today. I mentioned clean and smooth surfaces. One of the effects is the debarring, or taking away sharp edges and smoothing them. This is because the electrical field have a tendency to concentrate on sharp edges. This is an example of gears that you see here, the bars of manufacturing, and after electro-polish they all disappear, while keeping the shape of each tooth as meant to be originally. This electro-polish also creates very deep passivation, better corrosion protection. I will discuss this later. And there's a third fact that I want to emphasize. During electro-polish, there's electrolysis that happens in the electrolytic, and oxygen is released on the anode, helping the workpiece with the chromic oxide buildup, which is what we want. On the other hand, the hydrogen in the water or in the solution, or also in the workpiece, leaves the workpiece surface towards the cathode, and thus helping to prevent hydrogen embrittlement, which is like rusting, but not like rusting, yet another chemical process that can ruin the performance of metals. And once you perform electro-polish, you do not need to bake the workpiece again. You reduce the hydrogen and take it away such that hydrogen embrittlement is not happening. You can electro-polish all sorts of sizes. These are very big chambers, and these are very small pieces. Between 4 meters to a few millimeters, we can electro-polish all sorts of workpieces. There's no bending, warping, or distortion, contrary to mechanical treatment, which is nice. We have full control on the process by locating correctly the counter cathodes, which are tailor-made to each case. And we fully control the voltage, the current, the temperature, the time, and the composition and age of the solution. So we have full control of this process. As Professor Groysman mentioned earlier, there are all sorts of stainless steel alloys. These are the 5 families that, or 4 of the families that he mentioned: austenitic, which are not magnetic; ferritic and martensitic, which are magnetic; duplex, which are a combination of austenitic and martensitic; pH, which are precipitation hardening, and they all have similar but different electro-polish behavior. For austenitic, they are excellent fit to electro-polish, both in terms of corrosion resistance and in brightness. The classical 304 or 304 low carbon, 316 and 316 low carbon are very fit to electro-polish. There's one type which is an exception, 303, and I mention it later in the phosphor and sulfur constituents later on. So basically excellent for fit for electro-polish. Ferritic and martensitic are okay, they are good fit, but the result will be less bright. Here again, 416 and 440 require special electrolytes because of the phosphor and sulfur contents. Duplex alloys are excellent fit for electro-polish. pH are excellent fit, so you get both corrosion resistance and brightness, and also you get the hardenability in thermal processing. So pH alloys are readily ready for electro-polish. And a general comment for this phosphor and sulfur, they provide poor electro-polish performance. They require non-standard electrolytes. I will not get into this, but basically this is something that we need to control.
One moment, sorry, Dr. Herzl.
Yes.
Time is running out. Just 1 more minute, and we will have to finish the presentation to leave time to.
All right. So let me skip some slides. I will not talk too much about this salt spray chamber test, and I will also skip a little bit about this cleaning or disinfection. We know that in normal or mechanical polishing, we have scratches that can be shelters for organic materials. In smooth cases like Electro-Polish, these are not happening. Unfortunately, I do not have time to go into the details, but when comparing passivation to Electro-Polish, we see that the corrosion resistance improvement is better 30 times than passivation when you use Electro-Polish. This is due to the depth. And now I will very quickly touch some of the use cases that I meant, and please stop me whenever you think I'm over my time. So in one case, a customer was using our D100 solution to renew corrosion protection in the field, but he complained that this flows up of the treated surfaces, drips, and creates white stains. And we were able to tailor to his needs another formulation for this field passivation liquid to make it as a gel, which enables local brushing and adheres locally to the treated surface, so no flow of or dripping. I will not talk too much about bacteria or biofilm resistance. I will just mention that it is definitely following some researches that we did. Electro-Polish provide much augmented disinfection sensitivity, and this is one of the reasons why this is clearly the right solution for pharma industry or food industry. I'll talk a little bit about light energy reflection, and maybe this will be the last use case I will mention. So the customer came to us with a linear filament lamp located coaxially inside a stainless steel half pipe, which he wanted to be used as an energetic reflector. He wanted to maximize the reflectivity in order to enhance the radiation efficiency. So he was looking for a polishing and brightening process, and also asked for mirror-like coating on top of it. And then we said, indeed, specular or mirror-like reflection is optimal for creating optical images, but not necessarily for good volume or space coverage. If you see here specular reflection, this goes in one single direction. If you use other Lambertian or diffusive reflection, you can cover the space or the volume in front of the reflector. And in some cases, you can get a mixed or haze reflection. So clearly for reflectors, this is the solution of choice. And we came back to the customer and told him, yeah, we will electro-polish the reflectors, and this will enable the fill-up of the volume and avoid unnecessary focused images of the lamp filament. And then you do not need to silver coat it. We can save you the cost of it. And he actually tested it and verified the solution by radiation energy measurements. And indeed, Electro-Polish is a good process for treating reflectors. I will not get too much into 3D additive manufacturing because I know there's another lecture later on the webinar. So I will skip this fourth use case and just finish my presentation. I think we covered what I wanted. We skimmed over surface aspect, both phenomena, treatments, and applications. We dived into stainless steel and reminded ourselves with a trick of Chrome 2O3 oxide layer that protects from corrosion. We mentioned two methods like chemical passivation and Electro-Polish, and we got to know the advantages of one of them over the other. And we made actually 2 use cases instead of the 4 I meant to present. So with that, I will conclude, and thank you for your attention.
Okay, thank you very much, Dr. Yehezkeli, for this your interesting presentation. And the next speaker is Dr. Claus Qvist, who will talk about the use of stainless steel in pharmaceutical and food industry, hygienic design, and the old and new problems and their solutions. Dr. Claus Qvist is a chemical engineer, PhD, and corrosion specialist in stainless steel. Dr. Qvist is employed in Damstahl, Denmark, and serves as a technical advisor for both the company and all the customers. This includes solving corrosion problems, choosing the right steel grade, and anything else. Dr. Qvist, please, you can proceed with your presentation.
Thank you very much. Just one question. Can you hear me?
Yeah.
You can. Excellent. Yes, also thank you for allowing me into this fine company. What I'm going to talk about today, it's of course going to cover a little bit of what everybody else knows a lot about. It's a little bit about stainless steel, how it works. Dr. Herzl already told us about the oxide formation. I'm going to make this one short. Corrosion. I use whatever opportunity I have to talk about corrosion. But that's because corrosion is the basis of how stainless steel is working, why we love to use stainless steel in the pharmaceutical and in the food industries, and basically the basis of all of it. That's simply because it's so very nice and corrosion resistant. I'm going to talk a little bit about corrosion above water, which is highly underestimated, simply because the conditions above water are a little bit different from below water. And finally, with the food pharma glasses, then talk a little bit about mechanical surface treatment. Why do we actually insist on basically destroying the steel when the raw material is so nice? Stainless steel, as we've heard a couple of times, is an iron-based alloy, 10.5% chromium, and then maximum 1.2% carbon. And depending on which way we want to control either the chemicals resistance or the physical structure, we can add a lot of different elements, basically around 30 elements, all taken from the periodic table. Because we want to, you can say, you want to hone the steel into some useful direction. From a corrosion point of view, the 10.5% of chromium is by far the most important, because chromium has this really lovely ability to passivate, as we just heard, and this passivation film, usually mostly chromium oxide, technically keeps the steel separated from the medium, which is quite good. It works just like a paint, and the interesting part is always what happens to this paint if it's suddenly broken down. And in by far most cases, we won't even notice it. It simply makes a refinish. It just rebuilds itself. Maybe we lost a nanometer or so. No problem with that. And this is the very reason why, just this little black arrow, why stainless steel is so incredibly popular. Sometimes it doesn't work, I have to say. And in this stage, when we got to perfect repassivation, the steel has been proved a number of times. It doesn't leak any metal into the media, which is very, very important if we are making maybe insulin, we're making COVID-19 vaccines, we are making any kind of food, milk, we're working in butchery, whatever we are doing, the ability not to leak any heavy metals into the media is quite important. But sometimes it doesn't. We get a local activation in the middle of all the passive surface, and then we have a very bad combination, which is a small anode and a large cathode, and we get a galvanic coupling. and very quick local corrosion. And depending on the state of this oxide layer, we get actually 5 different types of corrosion. General corrosion is completely, you can say, it's superfluous within food pharma, because it only takes place in very, very strong acids, usually strong sulfuric acids, sometimes very strong bases as well, but mostly it's like a sulfuric acid problem. Intergranular corrosion is the type of corrosion which occurs if you have too much carbon in the steel. Then you get some weakening along the grain boundaries, and you get selective attacks along the grain boundaries. But these days, the mills are very good at keeping the carbon low, usually below 0.03%. So intergranular corrosion is a kind of an antique type of corrosion which doesn't really exist anymore. Pitching corrosion, on the other hand, is very, very common, corresponding exactly to the example I gave you before. Crevice corrosion, called them sometimes localized corrosion. It's the same, except for the fact that crevice corrosion takes place in, you can say, in narrow geometries where you don't have any convection and all transport is controlled by diffusion. And finally, stress corrosion cracking, it's a combination in between usually high temperature, the presence of chloride, and then static stress in the steel, usually from, for instance, welding. These three are the bad guys. The only one I'm going to go to talk a little bit of detail is that's the pitting part. And for all of these, especially the pitting corrosion, they originate in surface defects. And it's just like we talked about before, prior to this meeting, the fishing line always breaks at the weakest spot. So dealing with stainless steel, it's very important that we avoid such local weaknesses. But pitting corrosion usually takes place in water. Water at a pH between 2 and 12, that's a very wide range, you can have to say. As I said before, we get localized anode reaction, small anode, large cathode. We get a very small loss of material. Because it's so local, we get very quick penetration and speeds around 1 or 2 millimeters a month. That's quite common, sometimes much, much quicker. The very common type of corrosion, as I said before, is highly dependent on flaws and defects. So avoiding defects, eliminating defects with the correct surface treatment, that's a very, very good way of fighting pitting corrosion. Here we have, it's from an experiment from a test series we made together with the Technical University of Denmark. And this is actually a very fresh propagating pit. It's in a 4404, the 316L. And what we see here, it's simply a 50 micrometer hole, which is because the oxide surface broke down right there. It didn't repassivate, and suddenly we have this active area and the corrosion starts. Same here. It could be the same example. It's not from a practical example. It's from a water tank. This is a 3 millimeter different steel grade 4301, but it's very easy to see how local the attack is. So this is really a question of avoiding, you can say, the attack points for these local attacks. When do we get pitting corrosion? What's actually determining? Yeah, it's the steel. It's a question of which steel we're using, and it's a question of the medium. No surprise here. And the steel, the most important element, I said before, that chromium, the more chromium, the better. That's 100% certain. Molybdenum is even better. Get two arrows upward. Nitrogen, for some people, it's a kind of surprise, but especially in duplex steels, it's very, very important, and it actually gets 3 arrows. Negative side of nitrogen, that's that we are only naturally able to dissolve somewhere in between 0.2 and 0.3% nitrogen in the steel. But even 0.2% is actually quite effective. Nickel is very good for stabilizing the austenitic, the face-centered cubic structure. But when we're talking about initiation of pitting corrosion, it doesn't really matter. Finally, the number of impurities sulfur, phosphorus, could be carbon, could be selenium, silicon, and so the higher the amount of impurities, the worse, because these ones work as attack points. And we want to avoid these ones. We want to avoid weak parts of the fishing line. These three are normally the ones we focus on the most when you're talking about the positive side. The medium, chloride, salt, it's uniformly bad. The more chloride, the worse. The higher the temperature, it's exactly the same, worse. Corrosion potential, yeah, that's actually the cathode reaction. Anode reaction and the corrosion, that's the steel dissolving, the metal ions being oxidized. But the cathode, that's the one eating the electrons. Normally, in most cases, it would be oxygen. The higher the oxygen level, the worse. Sometimes, especially within food pharma, we have a tendency to, we like to keep our equipment clean. Both Dr. Groysman and Dr. Herzl have told us that, and we, especially these COVID days, has emphasized the importance of keeping things clean. And one way to do that is hydrogen peroxide. I missed a 2 here, by the way. I'll correct that. And active chlorine and a few more agents, normally strong oxidants, they are very effective in boosting the cathode and thereby actually become dangerous to the steel. pH doesn't have any big effect on the steel. The higher pH, the better. But what's very important is that pH has a tremendous effect on, for instance, oxygen reaction. So pH actually becomes quite important, and the pH 8 is definitely worse than 9, which is worse than 10. So finally, anything else could be all kinds of proteins or inorganic matter. If they don't affect either the chloride, the halogenates, or the cathode reaction, normally it doesn't really matter. Yeah, these two are the key ones. Then I was going to say a little bit about water and why is it so. That's a very underestimated part. I have to say this is from a Danish medical plant. All these tanks are 316 L4404, including all the tubes and pipes. But everybody, they pay interest to why is it very important how the medium is below water. And it is. But actually the water line is somewhere inside. So the inside of the tank, it may be below water. If the tank is empty, it's not. It's actually above water. But then we tend to forget that actually the outside is always above water. If it isn't, then we have a lot of problems. And what's the difference? Below water, we have an enormous supply of electrolyte. We have a lot of salts. We have no evaporation. We know the temperature. And so it's actually quite well defined. And if we don't know the chloride, if we don't know the temperature, that's just a question of a thermometer and the chloride analysis, and we know that. What about above water? Yeah, at the most, we have some splash, some steam, some fumes. Maybe we only have a very thin liquid film. We don't quite know the temperature. Sometimes we do, sometimes we don't. But if it's equipment standing on the outside, then we'll have some seasonal variations. We'll have some even within 24 hours of the day, we'll have some differences. And then we have a lot of oxygen. And then perhaps the most important difference is that below water, we have an infinite surface contact, which is regardless of the surface condition. And above water, it's very, very dependent on the surface condition. Usually the risks we have to take into account above water, as before, general corrosion, that's a sulfuric acid problem. Forget about that one. Intergranular corrosion, forget about that one. You buy low carbon steel and you'll never see that one. Crevice corrosion, we don't have any bulk phase, which means we don't have any crevice corrosion. Pitching corrosion, stress corrosion, cracking are quite reasonable risks, especially at, you can say, at slightly lower temperatures, high chloride. Usually pitching corrosion is the biggest one. If you have a higher temperature, And we don't talk like 400-500 degrees, it's just 100 degrees. There's a very good chance we're going to encounter stress corrosion cracking, and you don't want that. This is a very nice example of pitting corrosion, which is on it's actually taken in a hotel pretty close to the Danish coastline, the west coast, where we have an almost constant west wind, and it carries a lot of salt and making things stay bright. That's quite difficult. The picture to the right, by the way, it definitely shows the danger of smoking. Don't do that. Why is the surface so important when we talk about things above water? If we have a super fine surface and we soil it with some kind of product, it could be disinfectant, whatever it is, once we rinse it, we get an almost perfect process, no problem here. If it's finely ground or polished, then we'll soil the surface again, try to clean it. We don't get all of it off. There's still the residue, and of course, it's in the bottom of the ditches. Rough surface, a lot of residues. It's rough, a bit more open, then we are usually a little more successful. But you can see that the contact time is actually very, very dependent on the surface. And if this is not sufficiently convincing, then take a look at your own garage door or your house if you want to paint it, if it's a wooden house. What do we do before we paint it? We grind it, we polish using emery paper to polish the door. Why? Because then the subsequent layer of paint simply has a better adhesion. So actually we use it constructively when doing a paint job, but within pharmacy, within the food industry, we don't want the paint to be sticking. Actually, we want this one over here. Then a few words about the mechanical surface treatment. Whenever we're thinking about using stainless steel for any food pharma process, the first step is to basically pick the right grade of stainless steel. Ideally, we want to have a perfect corrosion resistance. We want it to be neutral to the media. It's described in the EU regulation 1935. And the choice of steel, especially within the pharma business, the 4404 or the 316L is very, very close to becoming a global standard. We have to focus on what we call good manufacturing process, whether or not we are welding, bending, forging, applying any kind of mechanical surface treatment. We wanted to make sure that the steel stays as stainless as possible. And this includes the choice of the ideal surface. From an engineering point of view, and that's me, I would like to have an optimum corrosion resistance. I would like to have the perfect cleanability. I'd like to have a low risk of bacteria. As I said before, the COVID-19 situation has really taught all of us that hygiene is maybe not what we thought it to be. And then finally, and that's a big problem, look nice. This is usually a matter of that's usually a case for the architects. They want it to look nice, but looking nice is not always the same as being functional. And this we see when we're talking about the various kind of surface treatment. Chemical, Dr. Herzl gave us a perfect run through the various chemical methods, some of them at least. So we'll just stick to the mechanical part. Whether we are grinding, we are brushing, we are polishing, we are blasting, there is a general rule, as we can say: the rougher the surface, the worse is the corrosion resistance. And this we can actually measure, which we did at the university quite a few years ago, where we're testing through a method called cyclic polarization, where we're testing various sheets made of 4301, the 304 class, and we measured the pitting potential in a dilute chloride solution. And we tested these 6 different surface treatments, glass blasted, a rough brushing, and then polished to grit 36, which is very rough, and down to 360. The corrosion resistance was a bit like this. And it's very easy to see that the finer the surface, the better is the corrosion resistance. And but then some people may say, okay, what if we applied the chemical surface treatment, then we get results like this. And then we should remember that the 2B sheets, which almost every single pharmaceutical or dairy tank is made of, that's actually pickles from the mill. So why do we polish a tank to grit 220 when actually the steel we bought at the mill is up here? That's not good business, but sometimes there are too many architects. If we take a look at the various electron microscopy photos of various surfaces, then we have the electro-polished. I completely agree with Dr. Herzl. This is the perfect surface treatment, but also the 2B, the cold rolled surface we get from the mill, is actually quite good. The third best, probably the polished and the glass blasted, is the worst. Unfortunately, the world has invented people, not engineers, the architects and designers, and they will definitely say that the glass blasted is the best, and then the polished and perhaps the electro-polished instead of the 2B. So this is really a conflict of interest. If you take a look at some focal microscopy, these are images, not photos. On the ground, 3 ground, glass blasted, and the 2B and electro-polished. It's very easy to see that the electro-polished and the 2B, they actually, this should be quite easy to clean, whereas cleaning out something in the ditches down here, it's foreseeable wrong. Nevertheless, still the architects and the designers, they really love to have these polished ones. I don't. But from a cosmetic point of view, these ones are very nice. From a functional, these ones are very nice. And economical, definitely doing nothing is actually a very good solution. Yeah, this is just a very nice example of a pitching corrosion experiment where we see, especially this ditch, it's just weakened the steel beyond repair. And this is where we get the corrosion, in this case, during a corrosion test. This is a very wonderful example, which is from a dairy plant in Denmark. No corrosion problems here. You can say, why did I show you this photo? Because somewhere to the right there was this tube of water, and as you can see, there's some rust, a bit of rust in the lower part. No rust on the back wall, no rust on the elbow up there. Take a closer look, it looks a little bit like this. The analysis showed that the back wall was to 4404 as expected. Quite good. Pitching resistance equivalent 23. This one was actually better. So why did the tube suffer from corrosion? Why didn't the back wall? And the simple reason is because the back wall was just a simple 2B surface, cold rolled, and that's a funny way of putting polished. And the tube was polished very fine, but it was actually rough enough for it to hold on to salt water and whatever was in the atmosphere. So polishing, it looks very, very nice, but it's actually not always to get a better result. Then people within food pharma, they have a tendency saying, yeah, if the RA is below 0.8 microns, this is great. So no, the cold rolled is actually quite good, but if you take a look at the other 3, shot peening, that's by bombarding the steel with hardened steel balls, polished with aluminum oxide. This one also is a little bit rougher. Can I have 1 more minute?
Yeah, sorry.
No
One
problem.
more minute.
So the shot peen one, because you can say it's apart from the cold roll is the best one of these four. But the shot peen is actually quite open, and it's very poor at holding on to bacteria and dirt and whatever, whereas the ground surface is actually no good. One of the reasons we see here, because this is actually a cross-section through grid 80, quite rough. This is a surface we try to describe with an RA value, which we can't. This is the profile we get if we measure it with a laser beam, and this is the profile we get if we measure it mechanically. And this is just no good. There's no way we can measure these pockets. Fortunately, a pocket like this is very likely to give crevice corrosion, and you'll never see that in a 2-hour test. So rough surfaces tend to perform better than they should. Just made a few different tricks. Try basically all the red ones are negative. You will have this one as a PDF, so don't worry about that. You'll have all of them actually. So basically, I don't like mechanical polishing. It's no good. Same with glass bead blasting. It's even worse. It's even more complicated. Lots of pockets for bacteria and for salts and all that. So basically, it's electro-polishing. That's definitely perfect. Otherwise, if you can afford electro-polishing, then don't do anything at all. So my time is running out. I'm sorry about that. Basically, chemical surface treatment is actually so much better than any mechanical surface treatment, unless using a very, very fine polishing. So just to conclude, it's a passivating material, stainless steel. The more chromium, the more molybdenum, the more nitrogen, the stronger is the oxide film. 3 major corrosion risks. Local weaknesses, no good. All kind of grinding and polishing is really great for inducing them. So don't, if you can avoid it. Very fine polishing improves it, but otherwise avoid this. Go for the chemical ones, especially electro-polishing. I really like that one. Further reading, this is basically what I've been doing. Unfortunately, these ones are in Danish. All of them are available in English. Some of them even in German. This is the final one. If you want some contact, I'll leave this one for you as well, so you can always get hold of me. And because Dr. Groysman, he mentioned something about fish, I think we should finish with a 24 kg Mekong catfish. This is basically what I have to say, unless you have some questions. We'll take that later, I guess.
Okay, thank you very much, Dr. Qvist, for your really instructive talk. And the last presentation for today will be given by the Dr. Tatiana Henrich, and she will talk about additive manufacturing for chemical process industry, opportunities and limitations. She studied in Moscow and Russia at MATE, in Russian State Technological University, named after Kiev. Her doctoral dissertation in technical industry, Braunschweig, Germany, was development of a new nickel-based superalloy, VDM alloy 780, based on alloy 718. She got the Hermann Blank Scientific Prize for the doctoral dissertation. He has a postdoc in the Technical University Braunschweig, Germany. And nowadays, she is manager, business unit mechanical engineering, tools and automotive at Fraunhofer Institute for Surface Engineering and Thin Films, IST in Germany. Please, Dr. Henrich, can you proceed with your presentation? Yeah. We have some technical issues, but right now, okay, good.
Can you see and hear me? Perfect. Thank you. So thank you very much. I'm really exciting to be able to present in this really interesting workshop some short overview about new technology or new technique, additive manufacturing, and give a bit another view on materials. And today it was really interesting for me to see or to hear the whole presentation, and for me it's really interesting to be the last, hopefully not least, because I would like to go also through some myths and fears about additive manufacturing, also connected to presentation before, and the first one of Professor Groysman with some aspects like stainless steel are the same, always the same. That's also something that I hear in our life. The nickel-based alloys are always the same, but one myth is true: nickel-based alloys are expensive or more expensive than stainless steel. But it would be in the end. Some of you or all of you knew a lot, hopefully, about additive manufacturing. And if we think about how new technology, it is a point to discuss. And but I would like to start. So I would like to start with a short introduction of VDM Metals. VDM Metals is a company based in Germany with some production in US. Our owner is this company of Acerinox, so we have a deep connection to Spain now. And if you think about nickel alloys or where VDM starts, usually we're starting in working. Then stainless steel, I hope, yeah, you can see my mouse, stainless steel ends. So in the whole market volume or material usage, we are in the niche, and maybe that explains why additive manufacturing doesn't come or haven't come through really deeply for application in some industries, because the main driver till now in IM were the alloys like nickel alloys, titanium alloys, stainless steel also. So 316 is a really common alloys there. But let's start about. So if we speak about additive manufacturing, and then why some of industries really deeply or applied the whole new technology in production, and which one not, we can see it here. So if you see the scale, that is the technical readiness levels, start from 1 to 1 basic manufacturing implementations or really proof on concept, the whole trials and research and investigation. It's some line between 4 and 5, so it leaves laboratory and go to technical scale, and from 7 till 10 we should see, or we usually see, industrial application. So if you think about additive manufacturing in some, or you see some parts, it's really smart, fancy, small parts that you can see in some fairs. And that is also why in some cases in medicine is really now is a part of production line. If you think about typical part size, like a hip joints or dental implants, that it's not really big parts. And because the individualization degree is really high, because each body, unique case, it's really helpful to use something as a technology and have an opportunity to produce really individual parts. For tools and molds is also common technology. In this case, also automotive use it for production. Why? Because the tooling production is also really expensive point of view. And in some case, it's difficult and take a long time from design, from maybe construction to implementation. In case of AM, it's easier to produce a part, so it was for a tooling production. With this technology, we can easily decrease the time or implementation time. So aerospace, these guys are main driver of additive manufacturing, because exhausting of common or well-known alloys and trying to implement the new design, something like cooling channels or structures for cooling, should help to increase of application temperature, and in these areas 5 to 10%, 5 to 10 degrees C increasing of application temperature, bring a big step in order to increase efficiency. In automotive industry is a bit more difficult, because the amount of parts for one production is so high, the production time, and this is a really cost-driven industry. So in this case, it's more find application for design and for high level or high end or racing cars, really real application. We can discuss, is it belongs really to automotive industry or not. In electronics parts, it's also point to use, but you can see here it's really in development stage. So here we didn't really see a lot about process industry or chemical process industry. Why? The first answer is the size of part. So if you think about some machinery and structure in this area, that it's really much bigger than 10 centimeter or 5 centimeter part. But with the development of technology, it also comes to a solution. So the biggest differences in additive manufacturing technology can be seen here. So powder-based or wire-based. And the most of research work and implementation work has been done in this area. And there are two parts, the bigger differences are laser-based or electron beam based. And electron beam based is focused on some reactive materials and like titanium alloys, cobalt chromium alloys, and find really industrial applications. So we can see here not all this medicine application, but also aircraft application. There are some parts produced from GE, which is now flying or using in civil industry. So if we think about laser-based, powder-based, laser-driven, so we have a big part in selective laser melting, SLM, or selective laser sintering. But also, if you think about the more bigger part, it comes to laser metal deposition. So powder size depends or can be produced usually through requirements of customers. And you can see here also typical alloys which are using in this application. So we can see here titanium, nickel, stainless steel alloys, and here more focus. In wire-based alloys, there are a lot of titanium, but in industrial application, we see a lot of demand in 316 alloy, in some case for production of tubes, if some material not available. In wire-based production, we have to think about that this is really 3D welding. And from this point of view, so we discuss the the chamber size or the part size. Here in this area, the new development comes now for 2 cubic meter with a till 4 lasers. And here is or in wire-based alloys, the chamber size could be till 3 cubic meters. So the production of bigger parts is available now, but here we should really also discuss, and we will do that later, which application and which requirements on your part, on material, on microstructure, and also on corrosion and oxidation resistant we have, and which circumstances in case of surface and or microstructure we produce during this technology. So if we speak about general classification of nickel-based alloys, I only like to discuss it with you because we come from niche application from most of you. So if we speak about wet corrosion alloys, you can see here the main system, like pure nickel, nickel copper, or also iron-based. So VDM portfolio starts usually we would say with 20% nickel inside. So we are producers of austenitic alloys in this area, with whole advantage and disadvantages that we have seen in presentations before. The main driver of additive manufacturing was or is aircraft industry, and they are here. And in the super alloys, why this alloy is called super alloys? Not because they're only super expensive. It is in this case, it's really super expensive, but because they have some phase, gamma prime phase, which cause high strengthening effect for higher temperature. These alloys, that is a different of structure here, polycrystalline, like a normal production way in road alloys. But here you can see some directional solidification. It means that the grain size growing in the solidification direction, or really single crystal. Single crystal means that small part, like turbine blades, is made only from one grain, and you can imagine that one part of one blade costs round about the new Golf car, just a German car Golf, and it's expensive, but that is a point. And special alloys like soft magnetic alloys or controlled expansion alloys haven't really see a lot of industrial or scientific interest in area of IM. So if we discuss the nickel-based alloys and really some conflict of interest for business case for additive manufacturing made from some management or economic point of view, and also technical point of view. And we can see that with increasing of this gamma prime volume, so gamma prime, this is nickel-free aluminum or nickel-free aluminum titanium niobium. Phase is really small, depends on microstructure. We have from 5% or less or nothing till 70% here. We see that the high temperature mechanical properties like creep and fatigue growing, the production costs increased or jumped high. Customization degree is also increased. That means that individual construction needs individual shape, and oxidation and corrosion resistant at high temperature also increased rapidly. But with these properties, and these alloys was trimmed, in this case, this cast alloys were really trimmed for end application. And requirements from another industry, like process industry, oil and gas industry, chemical process industry, they're also really focused on production, workability, and maintenance and service opportunities. Because if they think about cast alloys or single crystals, the point is they are no melting, no segregation, really high creep resistant, and in the end of the day, probably, or maybe it could be weldable, but weldable means repair welding here, not really construction welding. If you think about normal nickel-based alloys or wrought alloys for big application, we cannot imagine some heat exchanger without any deformation at all or welding structure. So that means that workability of these alloys is a focus on development and application, and not always the end properties like creep or oxidation resistant. Because to having one material which is perfect for some corrosion or oxidation environment, but if we cannot really weld it or surf it or make some maintenance work in the field, the feedback would come from end customer, usually interesting alloy, sorry, not really. And you can see here some examples of alloys which is used, or typical alloys for this application. Alloy 59 is the next generation of C alloys. It shows really strong improved of corrosion resisting in comparison to C276. Alloy 699XA was developed for application at high temperature corrosion called metal dusting. So if we have temperature range between 500 700 degrees C and a lot of carbon activity there. I hope that alloy 625 is good known, and alloy 718 is main or right horse in this area, and this comes to dreams. So these two alloys, the people from aircraft would be happy to print in a part, not really small wall, not a small cube with a 1 centimeter edge, but as a part, and it's really difficult. So this, or impossible now. So in this case, you can see all 5 probability to build the cracks, and you can speak about quality cracking if you'd like. But so if a chemical composition is extremely important also for choosing, or for choosing of business case for additive manufacturing, because usually we have a wide range in our alloys for production, and within the specification, some materials are really adjusted for production way or for end application, because you can see here silicon content. We discuss it also, and sometimes it's really helpful to have a silicon for some application, also corrosion application, but silicon is not really helpful for welding process. And it should be clear that before we start apply the new part produced by additive manufacturing, we should get the part. And that is a really not really jokes, but it's some ideas. If you go to boron concentration, it's really good for increasing of high temperature properties like stress rupture, because it's grain size active, grain boundary active element. But it's really detrimental in nickel-based alloys for welding process. So in case, yeah?
Okay, 1 more minute, sorry.
Okay, so if we speak about production and adjustment of chemical composition, you will see if we have some alloys, and also in stainless steel area, which were trimmed for many decades for end application. It's sometimes not always helpful to think that choosing the standard chemical composition would fit in area of AM. So that is a point that should be discussed or mentioned, and in this case really discussed with a material producer. how it's usually made is melting furnace. You melt your material in vacuum induction melting. You start to cast the material, and with a gas nozzle with argon, usually it's argon, you have the powder go down, and if it come to the end of the facility, is melted or solidified, and you can see here the powder. So I go through this point. It would be the PDF after, sorry for timing, so that is what we discuss. You should understand the whole production chain, because one chemical composition could work for one application but not for another, and that is the point for think about. We discuss a lot of surface. If we have one chemical composition which should work or well work during or after AM, and we also choose the process parameters that also work well for this chemical composition, we usually start, and how we're working with microstructure analysis, and think with start with standard heat treatment. Standard heat treatment shouldn't always fit to printed parts in comparison to raw parts. And after some evaluation, and if it fits, we go to material testing, compare it with forged material, and if it answer yes, we go to application. I would say here's this surface quality important. And surface quality important in case of, think about if we have some internal channel with difficulties to go in for example, polishing process, in really worst case, something like downskin, not optimized downskin parameters, we would have surface looking like this. And this surface usually is not really optimal if you have some fatigue or really corrosion environment there. How the powder look like? Is it for last slide that I'd like to show? Sometimes you see the differences in the powder. Really, shape or morphology of powder is important, but not too important. It's important to understand your process. This slide I would end in this case and show some alloys and powder in these alloys that hopefully interesting for application in chemical process industry, in consumer goods. And these alloys also show the really good process ability and ready to use and to apply for new geometry and new environmental requirements. So thank you very much for, yeah.
Okay, thank you very much, Dr. Henry. Sorry for the time, but
it's
very, very interesting and inspiring presentation so far, the presentation, and now we will give way to the question time for the audience. We have some questions here. The first question is, I think, for Dr. Jeheskeli.
Yes.
If there are tables or guides, values for permissible Hertzian pressure for different types of stainless steel?
I'm not sure I fully understand the question.
Yeah,
maybe if I read it.
Yeah, it's the first question. Jaume Beltral say that there are tables with rolling contact resistance, Hertz contact, crash stresses for stainless steel of various internal structures. For example, austenitic, ferritic, martensitic, and precipitation hardened type.
Maybe we should, I'll try to read the question, okay, and we can get back to it later. Okay.
Okay, we go to the next question. This question is for all the speakers. Are you thinking or planning the technical alternatives for the steel industry decarbonization?
Again, was this to me, this the question?
No, it's for all the speakers, I think. That means I think that the steel industry is by contamination with the of the process of the greenhouse effect, and then the question is about about alternatives to this this industry. I read something about hydrogen used for this industry to reduce the CO2 emissions, but I don't know if you have something to say about this topic.
Maybe I can comment it. So in some application, the nickel-based alloys can be used, but usually it depends on process parameters. And in some cases, it's not possible to have something that have a really long time application if the process parameters are really rush. And yeah, so that's it's should look for exactly process parameters and trying to figure out which surface treatment maybe if it's possible, and also coating system if it's possible, or chemical composition to find the best match.
Okay, thank you very much. There are many questions more, but to be answered. But I think looking at the time, that so we are already at the end of the time, and I would like to ask the last question. This is for Tatiana Henrich. In your opinion, which is the most promising new alloy for the near future for additive manufacturing?
I would say the most important success point is to choose a material which is good weldable, and good weldable means easy weldable. And from this point of view, start to build the construction and application case. So they are 718 or LO59. So if we have some difficulties during the welding process, if we weld some tube or try to produce a tube or some sheets connections, that would be difficult. If we have something like alloy 316L that is also widely used, it depends on application, but try to figure out alloy which is really easily can be welded. So that's maybe general answer.
Okay, thank you very much. And okay, thanks to all the participants and the speakers. Thanks to all of you who have connected to this webinar today. We are at the end of the time, not at the end of the questions. Yeah, to all of you who are connected and have questions that we are not able to answer because of the time, you will receive an email with an answer to your question. And so, having said that, thanks a lot for your participation. Thanks a lot to all the speakers for your time and for your interesting presentations. And have a nice day, and thanks for joining.
Can I have 30 seconds?
Yeah, okay.
Yeah, because there was a very general corrosion. If manufacturing will change, you can say, the corrosion performance or other properties, and I'll say basically yes. I mean, any kind of manufacturing, whether you're welding, like Dr. Hendrich told us, or you are bending, or you're stretching, or whatever you're grinding, you're polishing, you affect both the strength of the steel. Just cold forming will tend to harden all the austenitics. If you're into, you can say, the pH alloys or the martensitics, they're usually hardened by you can say some kind of thermal process. But all you can say, the construction steel, the ferritics, the austenitics, the duplex, all of them, they become harder when you tend to bend it. On the other hand, if you weld it, you make it quite, that's quite you can say it's a very powerful annealing. So you tend to soften the material. So it's very hard to, you can say there's no universal answer. The only, you can say yes, any single process will affect both the mechanical properties and the chemical properties.
Okay, thank you very much, Dr. Claus Qvist. I think that's all for today. Then I shall give having said that, thanks a lot again, and I finished this webinar. I think.
Okay.
What happened with Dr. Alec Groysman? I don't know, some technical issues. But okay, thank you very much for joining us today. Okay, hello, Dr. Groysman again. No,
on off.
Okay, have a nice day anyway, and thanks for joining.
Thank you very much.
Okay.
Thanks to you.
Thank you very much.